Hello there and welcome to this A-Level chemistry video about empirical and molecular formula. And in this video we will define empirical formula and also define molecular formula, and we'll explore the relationship between these two. We'll look at simple calculations for empirical formula, and then we'll extend that into how you can use the empirical formula to work out a molecular formula. And we'll finish by looking at two experiments. In the first one, we'll see how you can work out the empirical formula of magnesium oxide using the principles explored earlier. And we'll finish by looking at something called the water of crystallization and how you can determine the value for the water of crystallization using an experiment. So first of all then, the definitions for these formulae. Now, the empirical formula is the simplest whole number ratio of atoms of each element in a compound. And I have seen this be a 2-mark question in exams. And the molecular formula is the actual number of atoms of each element in a compound. So their definitions are really similar. It's just that the empirical formula might sometimes be a reduced version of the molecular formula. And so if we look at a few examples here, if we have these two molecular formulas, C2H4, and then this really complicated one looking underneath, the relationship between the molecular formula and the empirical formula is a simple integer division or multiple depending on which direction you're going. And the reason for that is that the empirical formula is the simplest whole number ratio. So if we have a look at the carbon to hydrogen, well, the ratio is 2:4 in the molecular formula. So can we simplify that? Yes, we can. We can simplify it down to 1:2. And so the empirical formula is CH2. And then in the same way, in this really complicated looking ratio over here, we can see that we've got this ratio, but all of these numbers are divisible by 3, and so we can reduce this down to the empirical formula C4H6Cl2O. And the fact that it's a simple multiple relationship between the two is really powerful and really helps you to remember in an exam. Just a few more examples. Here are some formulae. Can we simplify them into empirical formulae? And the answer is yes for the first one. That is a 2:6 ratio, which reduces down to a 1:3. The second one, yes, we can definitely reduce that as well, because 5:10 can be reduced down to C/2. That was the same as our first example on the previous page, by the way, so lots of things can share an empirical formula. 3:8 as a ratio cannot be simplified any smaller, so that means that it is both the empirical formula and the molecular formula, and that's perfectly possible. The nitrogen to oxygen ratio in the next one is 2:4, and of course we can reduce that down to 1:2. And then in the last two, the complicated looking ones, it's 2:4:2, and so we can reduce that down to 1:2:1. And then this last of all, 6:12:6, well, those are all three divisible by 6. And so we get, once again, C6 becomes CH2O. So now we've explored the relationship between those two types of formula, let's look at how you might actually calculate the empirical formula. So in this first question, we've got a hydrocarbon contains 1.2 grams of carbon and 0.4 grams of hydrogen, and our command is, what is the empirical formula? Now I strongly recommend you always follow this same pattern, and so the elements go here in columns, and so we've got the elements carbon and we've got the element hydrogen. And so the elements go there, and then down the side we always have the same 4 things. We have mass, and then we have relative atomic mass, and we have moles, and we have mole ratio. And so we can fill this in with the mass of carbon is 1.2, the mass of hydrogen is 0.4. The AR of carbon is 12.0, the AR of hydrogen is 1.0. So the moles is 1.2 divided by 12, which is 0.1, and 0.4 divided by 1, which is 0.4. And so we can tell this one by inspecting is a ratio of 1:4. So 1 carbon for 4 hydrogen. So the empirical formula is CH4. Where you can't just tell by inspection that the ratio is 1:4, you need to divide by the smallest number. So 0.1 moles divided by 0.1 gives us 1. and 0.4 moles divided by 0.1 is equal to 4. And so we get our ratio of 1 to 4 this way instead. This next example is really similar, except it has got one extra complication. So let's read it. 24.5 grams of an oxide of phosphorus contains 10.7 grams of phosphorus. What's the empirical formula? Well, we know that obviously we've got phosphorus involved, so that is our first element. And the first pitfall is to forget that the other element is involved, and that is oxygen. And then we've got our mass, AR, moles, and mole ratio down on the side. And so we've been told that we've got 10.7 grams of phosphorus, but they haven't told us what mass of oxygen that we've got. And so we need to do a subtraction. 24.5 subtract 10.7, and that's going to give us 13.8 grams of oxygen. And so that is our first mark, really. This would be worth an extra mark compared to the previous one. And the relative atomic mass of phosphorus is 31, and of oxygen it's 16. Both of those 0.0 to 1 decimal point. And so to calculate the moles, we have got 0.352 for phosphorus, and then 0.863 for oxygen. Now this one's a lot harder. We can't tell by inspection what the ratio is. So the trick here, and we could have done it on the previous one, is to divide it by the smallest, because anything divided by itself is going to be 1. So the phosphorus is going to end up being 1.352 divided by 0.352. That gives us 1. And 0.863 divided by 0.352 will give us another number. Now this time it's not a whole number. It is a ratio of 1 to 2.5. Now the absolute thing that you must not do is round this up to 3 or down to 2. What we need to do is we need to scale it, and so 1 to 2.5, if we double both of those numbers, that becomes a 2 to 5 ratio. And so the formula of this oxide of phosphorus is P2O5. And so that's definitely something to watch out for, rounding up far too much. This example is an extra complexity because we've been told it's a hydrocarbon and it's got 84.2% of carbon. What's the empirical formula? Now, first of all, since it's a hydrocarbon, it needs to contain hydrogen as well as carbon. And so hydrogen is going to be the percentage that is missing, and carbon is our 84.2%. Now, we've got mass, and then we've got AR, then we've got moles, and then we've got the ratio down the side. And so at face value, it looks like we haven't got the right information, but we can treat percentages as mass, because if you had 100 grams of this particular hydrocarbon, you would have 84.2 grams of carbon. So what we can do is we can consider this mass to be either mass or percentage. It doesn't actually matter. And so the carbon is 84.2% and the hydrogen will be the rest. So 100 subtract 84.2, which is 15.8%. And then the AR of hydrogen is 1.0, carbon is 12.0, moles is mass divided by AR, so hydrogen is 15.8 divided by 1, which is 15.8, and the carbon is 84.2 divided by 12.0, which is 7.02. This one we can't tell by inspection what the ratio is, so we divide it by the smallest, which is 7.02. We can tell that this one on the right-hand side will be 1 because we're dividing it by itself, but on the left for the hydrogen we get 2.25. Now again, that's too small to round. I don't really want you to be rounding by more than 0.1, so 2.09 maybe could have rounded down to 2, and 2.91 could have rounded up to 3, maybe, because these are integer relationships between the empirical formula and the molecular formula. But here, definitely, this is too big to round up. So we need to find a multiple. And so to find a multiple, 0.25 is a quarter, so that means we need to multiply this number by 4, and this number also, therefore, gets multiplied by 4. And so we've got 4 carbons, and we've got 4 times 2 is 8, and then here we've got 9 hydrogen. And so the empirical formula is C4H9. Now remember that the molecular formula is an integer multiple of the empirical formula. So if you know what the empirical formula is and how heavy the molecular formula is, we can work out the molecular formula actual. So we've got two examples here. A molecule has the empirical formula C3H5O2 and a relative molecular mass of 146. What is the molecular formula? Well, there's two steps here before you can give a final answer. And the first is to work out the mass of the empirical formula. And so 3 lots of carbon is 36, 5 hydrogen is 5, 2 oxygen is 32, and we add those together and we get 73. The second step is to find out what the molecular formula to empirical formula ratio is. In other words, how many times bigger is the molecular formula than the empirical formula. And to do that, it is simply the MR divided by the mass of the empirical formula that we've just calculated. And so the MR is 146. We've just calculated the empirical formula has a mass of 73, and so our answer there is 2. And what that means is that the molecular formula is twice as big as the empirical formula. And so our final task is to state that the molecular formula is C6H10O4, because that is twice as big as the empirical formula that we were given up here. We're simply doubling 3 to get 6, double 5 to get 2, double 2 to get 4. If we have a look at this second example, a molecule has an empirical formula C2H6O and an MR of 92. What's the molecular formula? Well, step 1, what's the mass of the empirical formula? 24 for the carbon, 6 for the hydrogen, then 16 for the oxygen, and that gives us a mass of 46. Step 2, what's the molecular formula to empirical formula ratio? Well, the MR is 92, the empirical formula mass was 46, and so the ratio is actually once again 2, and so the molecular formula is simply twice as big as the empirical formula, and so C4H12O2 is our final answer for the molecular formula. One example of a question that combines those two stages then, we've got a hydrocarbon that contains 3.17 grams of carbon, so carbon is one of our elements, and 0.528 grams of hydrogen. So hydrogen is our other element. And so we need our mass, we need our AR, moles, and the ratio. I'm doing it a little bit smaller because there's a part 2. So 3.17 grams of carbon, 0.528 grams of hydrogen, AR 12.0 and 1.0. When we calculate the moles, 3.17 divided by 12 gives us a moles of carbon of 0.264. Hydrogen is 0.528 because we're dividing it by 1. And then the ratio, we need to divide them both by the smallest, which is 0.264. And so we get 1 for the carbon, and we actually get 2 for the hydrogen. So the empirical formula is CH2. We've been asked for the molecular formula as well, and so doing those 3 steps as before, the empirical formula mass is 12 plus 2 for the carbon and the 2 hydrogen, so it's got a mass of 14. Step 2, what's our ratio? Well, the MR is 56, and 14 is the empirical formula, so 56 divided by 14 is 4. And then finally then, that means our molecular formula is the empirical formula multiplied by 4, and so C4H8 is our final answer for the molecular formula. Now there are ways of making this more complicated, but mostly they just involve adding a third element to the calculation. And if that was the case, you would just have this extra element over here, you'd have another mass for it, another AR, and you'd work out moles, and you'd just have a ratio that involved 3 numbers rather than 2. And so the formula would just be extended to maybe include an oxygen rather than just carbon and hydrogen. But the principles are exactly the same. The only thing that's difficult really is it's maybe a little bit harder to spot what the smallest mole number is that you need to divide all of the others by. Let's look at putting these ideas into practice now by exploring 2 experiments. And in this first experiment, we'll be looking at how we can calculate the empirical formula of magnesium oxide. So to do this, you start with the element magnesium in a crucible, and you heat it, and that magnesium will start to burn. And when it burns, it combines with oxygen to make magnesium oxide. And provided you precisely burn all of that magnesium and you don't lose any of the magnesium oxide as smoke, so we have a lid on our crucible, then this experiment will work perfectly. Like I say, those two errors that they sometimes ask you about in an exam, you can lose mass by lifting the lid and leaving it off for too long, or you could not fully burn the magnesium. Now, the data that you would need to collect during this experiment is to do with the masses. You would need to know the magnesium mass at the beginning, and you would need to know the mass of the magnesium oxide at the end. And once you've got those two pieces of data, you can work out how much oxygen, what mass of oxygen has joined with your magnesium. That's just a simple subtraction. So you can see that the final mass is 4.98, that's with the magnesium and the oxygen, and we need to subtract the 3 grams from it that was just the magnesium by itself. And we find out that we've added 1.98 grams of oxygen. And then we need to set up a calculation in exactly the same way as we've been doing for the others. So we've got magnesium and we've got oxygen. We have got 3.00 grams of magnesium and 1.98 grams of oxygen. That is our mass. The AR is 24.3 for the magnesium, 16.0 for the oxygen. The moles of magnesium, 3 divided by 24.3 gives us 0.123 moles. And for the oxygen, 1.98 divided by 16 gives us 0.124. Now, the mole ratio, when we divide by the smallest, we get 1 for the magnesium oxide because that is the smallest. Then for the oxygen, we get 1.008 as our ratio. Now this is close enough to 1 to round down, and so we can say that the ratio is 1 to 1. And remember, the question was, what's the empirical formula? And that is MgO. There is one of each of them. And also remember that this is an ionic compound. We don't have to work out empirical formulas for molecules. So we've got a metal magnesium and a non-metal oxygen. And so what we've calculated here is the ratio that the metal ions and the non-metal ions combine in an ionic compound. And of course, because this isn't a molecule, we couldn't follow up and ask a molecular formula calculation, because that would be ridiculous, because it's not a molecule, it's an ionic compound. We're going to finish this video off by looking at something called water of crystallization. Now, the water of crystallization is the water found in the crystal structure in the framework of an ionic compound. And so remember that ionic compounds are ionic lattices with alternating positive and negative ions. And so what this means is, for, in this example, iron sulfate, for every 1 iron ion and 1 sulfate ion, you will find 7 water molecules inside that crystal structure. And then in the same way, but a different number, for every 1 magnesium and 1 sulfate ion in magnesium sulfate, you will find 6 molecules of water locked in that crystal structure. And these are called hydrated salts, or hydrated magnesium sulfate, or hydrated iron sulfate. And what you can do in A-level chemistry is you can carry out an experiment in order to find out what this value for water of crystallization is. And you may already have done this. And in this experiment, what you do is you get a crucible with some sulfate, and so let's make this copper sulfate. And quite simply, what you do in this experiment is you warm the copper sulfate crucible, and what happens is, over time, water will leave. And it's this water of crystallization that will leave the substance, so it leaves the crystal structure. Now, do be careful, it's not evaporating, because evaporation is what a liquid does, and this isn't a liquid. So this leaves the crystal structure. And so what we're left with at the end is anhydrous copper sulfate, so copper sulfate that has lost all of its water. And so then in this experiment, what we've done is we've removed all of the water of crystallization from the copper sulfate. And so provided we know what the mass of the hydrated copper sulfate was at the beginning, and provided we weigh the copper sulfate at the end, we can work out how much water has been driven away during the heating. And we can also therefore work out what the mass of the copper sulfate is without any water. And using these two numbers, we can work out what the water of crystallisation for copper sulfate is. To make sure you removed all of the water from the copper sulfate, what you would actually do is you would take an initial mass for the hydrated copper sulfate, you'd then heat it, reweigh it, you'd heat it some more, and then you'd reweigh it, you'd heat it some more and you'd reweigh it, and you'd keep heating and then weighing until you got a constant mass for 2 consecutive measurements. And what that means is you have heated and driven away all of the water that there is to be lost. And this, just like with the magnesium oxide example, is called heating to a constant mass. And so if this was the experiment results and we had collected 6.864 grams of the hydrated copper sulfate, and we had then heated it and removed water, and at the end the anhydrous copper sulfate had got a mass of 4.389, we can then use these data to calculate the mass of water that has been lost, because it is simply the difference between the two. Because the hydrated copper sulfate contains water, the anhydrous copper sulfate has lost it. So then we know the mass of anhydrous copper sulfate and we know the mass of water that has been lost. And so to find the water of crystallisation, it's exactly like an empirical formula calculation. You treat the copper sulfate as a single entity with a mass of 4.389 grams. Then its MR is 159.6. The water, again, 2.475 grams with an MR of 18. And so the final step here is to work out the number of moles. And we get 0.0275 for the copper sulfate and 0.1375 for the water. And finally, we need to turn this into a whole number ratio where copper sulfate will always have a 1 and the x will be an integer that will always be equal to or greater than 1. And we have to divide by the smallest to get this, and so for copper sulfate we get 1, because 0.0275 divided by itself is 1, and then 0.1375 divided by 0.0275 is 5, and so the final formula is CuSO4.5H2O, because that is the water of crystallisation of copper sulfate, 5 waters for every 1 copper sulfate. Okay, that's the last thing in this video. Thank you very much for listening. I'll see you next time.